Hi everyone. In this video I'm going to talk about the three-phase synchronous motor, how it is constructed and how exactly does a synchronous motor work and why is it called a synchronous motor in the first place. To find out, we are first going to look at how a synchronous motor can turn and how a rotating field is generated. So let's start with this drawing over here, in which we have the stator, the fixed part of the motor over here, and this is the rotating part, also known as the rotor. And it's a three-phase motor, so we have three phases, three coils over here. This is coil A, this is coil B, and this is coil C. And these coils are connected at this point over here, and that is what we call the neutral. And these three coils are connected to the main supply voltage, the three-phase main supply voltage. So we have three sinusoidal voltages which are separated electrically by 120 degrees. And these three sinusoidal voltages generate a sinusoidal current in each phase. And these currents are drawn over here. So this is the current flowing in phase number A, this is the current flowing in phase number B, and this is the current flowing in phase number C. And you see that also these currents are, have a phase shift of 120 electrical degrees. These currents generate a flux into this phase, and that magnetic flux generates the complete magnetic field, so that is generating the motor torque. So let's start off with judging what is happening at this point. So in this point we have a current flowing in phase A, which has a maximum value over here, and the currents in phase B and phase C are negative and have half the amplitude of the current in phase number A. So also the flux generated in phase B and in phase C have half the value of the flux generated in phase A. So we can draw this by drawing flux vectors, and this is the positive flux vector generated by the current in phase number A, and these are the flux vectors in phase B and phase C. And you see that these flux vectors have half the length of the flux vector generated in phase number A. So now let's look to the total flux generated in this situation, which is the addition of this flux vector plus that one and that one. And remember, these angles are 60 degrees. So when this is 60 degrees, then this angle must be 30 degrees. So the contribution of that flux vector into this direction is 1.5 times the flux in this vector, because of the length, times the sine of 30 degrees, which is also 0.5. So it's 0.5 times 0.5 times the length of this flux vector, which is 0.25 times the length of this vector. Also for this flux vector, the contribution into that direction is 0.25 times the flux in this vector. So the total flux in this situation is 1 plus 0.25 plus 0.25, which is 1.5 times the flux in this phase over here. So now let's look to another point, 60 degrees separated from the original point over here. And in this point, the current in phase A has its maximum value but is negative, and the currents, in phase C. And the currents in phase A and phase B have a positive value, but half the current value of the current flowing in phase C. So we can draw in this situation also the flux vectors. So we have the maximum flux vector in phase C over here, and these are the flux vector generated in coils phases A and phases A and B, I should say. So the total flux in this direction is the addition of these flux vectors, which is again 1.5 times the flux generated by this coil over here, so generated in phase number B. 60 degrees later we have the same situation, but now we have 1.5 times the flux generated in this phase in that direction. And so we can proceed and go on and go on and go on until we are back at 360 degrees over here. So at every point we have a total flux at the stator. So at every point of the stator we have a total flux which is constant and which is equal to 1.5 times the maximum flux generated in one of the phases. So now we can model this as a so-called fictitious magnet which is moving around the stator. So we have a fictitious magnet, which isn't there of course because we have three electrical phases, but they generate a constant magnetic field at the circumference of the stator, which is 1.5 times the flux generated by one of the phases. And that magnetic field has a speed which is constant and is called the synchronous speed ns. So now we have modeled the stator, but we can also look to the rotor. And for a synchronous motor there is also a magnet in the rotor, and it could be a fixed magnet for small motors, but often for larger motors it is an electrical magnet. So here we have a two-pole motor with three phases, phase A, phase B and phase C, and one magnet in a rotor, and that magnet has of course two poles, north and the south pole, so this is called a two-pole motor with three phases. But there are also multiple synchronous three-phase motors, and we can more or less see how that works by cutting this stator over here and then bend it over, and then we can put another stator at the same position, and then we have more or less a four-pole motor because we have three phases, still three phases, phase A, phase B and phase C, but we have two magnets in the rotor over here, so four poles. We could also say two pole pairs, so two north poles and two south poles. But we can also see that during a period, now the speed of the rotor is not one rotation during one period of the magnetic field, but is only half a rotation. So we can calculate the synchronous speed of a synchronous motor by multiplying the frequency of the rotating field in the stator by 120 and dividing that by the number of poles in the rotor. We can also say it's equal to the frequency of the electrical field in the stator, which is 50 Hertz or 60 Hertz. Multiply that by 60 and divide it by the number of pole pairs. So a four-pole motor has two pole pairs. One magnet also always has one north pole and one south pole. So now let's look to another important definition of the synchronous motor, and that is the torque angle. Because we have seen that we can model that motor by a fictitious magnetic field, so a fictitious magnet which is rotating in the stator. That the rotor now also rotates synchronously with the rotating field, but the magnet in the rotor lags the rotating field by an angle which is equal to delta, and that is what we call the torque angle. Because you can imagine that when there was an absolute alignment between the fictitious magnet in the stator and the magnet in the rotor, there would not be a motor torque available. So the higher the motor torque, the higher the larger the torque angle, so the angle between the rotor magnet and the fictitious magnet in the stator will be. And that is what we call the torque angle. So that is depicted in this figure by this angle. So the maximum motor torque will be realized when this torque angle is at 90 degrees, so it's at that point. So the fictitious magnet pulls the rotor magnet, and that causes that torque angle. So the speed of the rotor is synchronized with the speed of the fictitious magnet in the stator, as discussed earlier, but it always lags, the rotor always lags the stator magnet by the torque angle. So having that, we can put it in another way by looking to this graph, and in this graph we see that it's a sinusoidal curve of the load angle with respect to the maximum torque, and the maximum torque is generated at a torque angle of minus 90 degrees or plus minus degree. Or plus 90 degrees. So again, when this magnet is perpendicular to the stator magnet over here, then we have the maximum motor torque, which is at that point or at that point. So at this point, when we have that pure alignment of the rotor magnet and the stator magnet, there is no torque available by the motor. And in normal situation, that torque angle is often somewhere between 27 and 37 degrees. But because we always have to generate the motor torque, of course, because we want to load that motor with the system we want to move. All right, and now we can also draw one point of our so-called torque speed characteristic or torque speed curve, in which we have the speed or the angular speed at the horizontal axis and the generated torque at the vertical axis. And we see, of course, that at the synchronous speed over here, we have a maximum available motor torque, which is at that phase angle, that torque angle of 90 degrees over here. And when the load is, of course, higher than the maximum motor torque, the motor will get out of sync. So this is the part of the torque speed characteristic we can draw. Now we are going to look to the model of a synchronous motor, and of course this is a three-phase synchronous motor with three equal phases, so we can look to the model of one of the phases, and this is that model of the electrical model of one of the phases, in which this is the main supply, the electrical source, generating a sinusoidal voltage E. And this is the model of one of the phases of the synchronous motor, in which we have a coil, an inductance over here, and of course there is also a resistor over here, but that resistor is compared to the impedance of the coil has such a small value that we can neglect it. So we simply model the motor by a coil and inductance over here. But also in this stator of the motor, an electrical field is generated, which we call the back EMF. And the back EMF is caused by the moving, rotating magnet in the rotor, which is often an electrical magnet, so generated by an electrical current in that electromagnet in the rotor. So that generated flux generates that back EMF. So we have a voltage from the mains, we have an inductance with an inductance voltage EX over here, and we have the back EMF voltage over there. And you can imagine that the higher the rotating speed will be, the higher the frequency of the back EMF will be. But also the amplitude of the back EMF voltage is depending on the rotor speed, because the lower the speed of the rotor will be, the lower the induced voltage will be, so the lower the back EMF voltage in this situation will be. So E0, which is the back EMF voltage, is speed dependent, both in frequency and in amplitude. So now we can see that according to Kirchhoff's law, the voltage E is equal to the voltage across the inductance, EX, plus that back EMF voltage E0. But remember, these voltages are not in phase, so we have to use a phasor diagram, which is shown over here. And I've put the mains voltage E on the horizontal axis over here. And we have seen that the rotor lags the rotating field in the stator by the torque angle delta. So also the back EMF voltage is lagging the voltage E by that torque angle over here. So E0 lags E by the torque angle over here. Due to Kirchhoff's law, we can say that Ex, the voltage across the inductance, is equal to the mains voltage E minus E0, the back EMF voltage. So we can draw that over here. Ex is E minus this voltage, that back EMF voltage, which is equal to this vector over here. So this is Ex, the voltage across the inductance over here. So we can also put that vector over here. Last but not least, we know that the current flowing in an inductor always lags the voltage across that inductance. So the current flowing in this circuit, so flowing in one of the phases of the synchronous motor, lags the voltage across the inductance by 90 degrees. So I is drawn in this situation over here. And we see that this current also lags the voltage over here. So we can say the power factor due to this angle is not equal to 1, because the power factor is the cosine of this angle over here. In Europe we also always call that phi, so we talk about the cosine of phi, and in America we often call that angle theta, so it's the cosine of theta. But the cosine of this angle is always called the power factor. So the current is lagging E over here, so this is a model of a resistive inductive load. So now we can also use that synchronous motor in another way. We can use it as a so-called synchronous capacity, because this was the model of one of my phases, and we have seen that that back EMF voltage depends on the value of the flux over here. So when the current in the rotor is increasing, the flux is increasing, and also E0 is increasing. So we can adjust that E0 vector, and I've drawn that over here. So this is a normal situation which we discussed previously. So we have E0 lagging always E by the torque angle delta over here. We construct the voltage Ex over here by subtracting E0 from E, and then we can construct the current through this phase by using the 90 degrees angle of the voltage across the inductor and the current flowing through that inductor. And then we have a normal resistive inductive behavior. But when we change the flux in the rotor over here, so when we increase the flux over here, we increase the back EMF voltage over there, so we get a larger phasor vector of E0 over here. And then let's look what happens. We can construct Ex again by subtracting E0 from E, so Ex is now in that direction, so the current through the inductor is in that direction. Remember, this has to be 90 degrees. So now we see that the current in this circuit leads the mains voltage by this angle theta over here. So instead of the current lagging the voltage E over here, it's leading the voltage E over here, which is more or less a capacitive behavior. So we can use this motor by increasing the field over here, so increasing the back EMF. We can use this in synchronous motor more or less as a synchronous capacity. So we can use that for cosine, theta, or power factor increasement. So improvement, I should say. So you can improve the power factor of your system by using a synchronous motor as a synchronous capacity. Alright, now the last thing I want to discuss with you is starting up a synchronous motor, because we have seen that we have one point at this moment defined of the torque speed characteristic, and that was the point at the synchronous speed. But the problem is that at startup the rotor does not start moving because of the inertia of the rotor and because the rotating field is immediately at full speed. So there is no starting torque. So we know that at the synchronous speed we have the maximum speed, but we have not a starting torque, so we have to come up with a solution for the motor to start up. And one of the solutions is that we use an induction cage, so-called squirrel cage, from the induction motor, so also known as the damper cage with damper bars. So the motor will in that case start up as an asynchronous motor, so as an induction motor, and when it comes at the synchronous speed, the voltage generated in the squirrel cage is almost zero, and then the motor again behaves as a synchronous motor. So this is what you often see, a combination of a synchronous motor, so rotor with a electrical magnet in the rotor, but it also has a squirrel cage for starting up purposes. Well, there are also other solutions. What you also can do is add an auxiliary motor for starting up that motor, or for instance use a frequency inverter with a startup function. Okay, well, that was quite a lot. I hope you enjoyed it, and I hope to see you in the next video. Thank you for watching, and see you next time.